Hello, everyone. Welcome back to the Hodge Theorem. So before we begin with new material, I want to go over what we did last time, as what we're going to do this time builds off of that. But just sort of in words. So the first thing that we did last time was introduce our setting. So we're working on a compact complex manifold with a Riemannian metric. We also introduced what it means to be a PQ form and what it means to be a square integrable PQ form. We also introduced our Sobolev spaces of PQ forms, and because we're working with the L2 norm for those Sobolev spaces, they're Hilbert spaces with their norm, the Sobolev space norm, which involves summing over the weak derivatives that you have in that space. So next, we also defined our differential operators and how they acted on PQ forms. So here we have a D bar operator and a D bar star operator. One thing that I didn't mention, because I didn't write down the formula for the D bar star operator, is that the D bar star operator is also a first order differential operator that takes a derivative in terms of holomorphic coordinates as opposed to anti-holomorphic coordinates. But it's a little bit more complicated than just the round D derivative. We then used a functional analytic tool to define a box Laplacian on an extension of smooth forms, smooth PQ forms. And this is the operator that we will be stating the Hodge theorem in terms of. So the way that we defined it, it is a self-adjoint operator. And then we ended last time by stating the Hodge theorem. So we have these three parts. The first deals with harmonic forms, which we defined. So
sorry, are you scrolling through things? At least on my screen, I don't see what you're referring to.
I am. Is it not? That's very strange. Let me reshare. Okay. Now we're scrolling. Okay.
Great, thank you.
All right, so now we have our expression for our box Laplacian on smooth forms. We extended it using this Friedrichs construction, and we stated the Hodge theorem. The first part of the Hodge theorem has to do with results regarding harmonic forms, which we defined as the kernel of our box Laplacian. The second has to do with finding solutions to the equation box theta is equal to phi. And the third part has to do with our green operator, which is going to be the way that we invert the Laplacian off of its kernel. Okay, so all of this setup just allowed us to define our box Laplacian and state this theorem. But now, before we prove the theorem, we need some analytic results. So that is what we are going to be talking about today. So chapter 2 is the analytic results. And for these, I'm not, oh man, my handwriting is still super messy on this. I apologize. I will try to keep it, I will try to improve from last time. I will not be proving these results here. The proofs are highly non-trivial. These results are each big in their own field. This is just one application of them. In some cases, I might talk a little bit about how the proof goes, and that's mainly to give you a better understanding of what the result means, because the way that I'm going to state them might seem sort of technical, and in order for you to get out of this talk the meaning of the result, I want you to know, like, okay, well, this is how the proof goes, and that helps you understand why these technicalities are there. Okay. So first, we're going to start with, oh man, Sobolev space theory. And I'm going to state these results for functions, but the statements can be generalized to forms using the same constructions that we've used to define this Sobolev spaces of PQ forms. So the first result, oh no, is the Sobolev embedding theorem. And this states that the inclusion map from the S, so HS on RM, into CK on RM is bounded if and only if S is bigger than K plus M over 2. And additionally, if this holds, the weak derivatives, the weak derivatives of F in HS up to order K are bounded, sorry, not bounded. They are ordinary derivatives, so not just weak derivatives, but they are actual derivatives. And this is maybe after altering on a set of measure 0. Okay, so what this means is that if you have enough weak derivatives and you're also satisfying this condition, which is really a statement about the dimension of your space, K of those weak derivatives are going to be real. And so this is the result that allows us to translate results about Sobolev norms and being an element of a certain Sobolev space into actually being a smooth element. Yeah, okay. The next theorem that we're going to use is the Relic compactness theorem. And this states that for each relatively compact open subset K in RM and a pair of real numbers S and T such that T is less than S, the inclusion, which puts our space with more weak derivatives into our space with fewer weak derivatives, is compact. So this inclusion is a compact operator. And note that we're also assuming that our space, so this is true for relatively compact sets. In our case, we're considering only compact manifolds. So we're going to be able to use this theorem in a particularly nice way. But essentially what this is saying is that you have a space with more weak derivatives, you can include that into a space with fewer weak derivatives, and that inclusion is compact.
Emily?
Yeah?
Can you remind us what H0S of K is?
Yeah, so this is, I actually have, okay. So H0 S of K is the space of functions with S weak derivatives such that the functions how to order this. Functions f such that this norm is bounded. So this is d alpha f 2 squared. This is the L2 norm. And this is equal to, you write this as this is finite. And the 0 means that we're taking these functions also to have compact support. So yeah, that's what that means.
Thank you.
Mm-hmm. Okay, so we're not quite done with our Sobolev space theory, but before we state the last sort of corollary, we're going to have a digression into what will begin our discussion of smoothness, of the regularity of the solutions to our box equation, our box operator. And this is called Wordings inequality. So I'm going to write this down and I'm going to sort of explain what this means. And I'm going to talk a little bit about how you prove it. So we're taking X to be a compact Hermitian manifold. And and for each compact subset of X, there exists a constant dependent on that subset, which is positive, such that for all smooth PQ forms, theta supported on K the Sobolev 1 norm of theta is actually bounded by this constant times this Q norm, which on smooth forms is this guy, our box operator plus the identity of theta, theta. And this is, this inner product is just the L2 inner product on our space. Right, and so the Sobolev 1 norm we defined in terms of forms as well, but it's the sum of the L2 norms of the weak partials of order 1 or less. Okay, so what this is doing is it's relating our differential operator, our box differential operator, and the norm we get with that, this Q norm, to the sort of standard weak derivatives that we consider when we're defining the Sobolev space. And this is going to allow us to turn our interpretation of solutions to this box operator, things that live in this sort of Q Hermitian space, into results regarding regularity in the Sobolev sense. The way that you prove this is you write down what this box operator is going to look like for smooth forms, and then you do a lot of, maybe not a lot, but you do some integration by parts, you do some bounding tricks, and you just, this is just what it is. I was thinking about writing down the actual equation for d bar star before, or the expression for that, but this is where you would use that equation. You would use it to sort of do this proof, and I wasn't intending to do this proof because I don't necessarily find it to be illuminating for the Hodge theorem. Okay. So once we have this, which is, again, this relationship between our Q norm and our Sobolev 1 norm, we can actually make a statement about the domain of our box operator, or this is our F operator. So we've defined box to be F minus the identity, where F is given by the Friedrichs construction, and F is equal to the identity plus box. And this is especially true, this is true in the like straightforward sense on smooth forms. Okay. So what follows is a statement about the domain of our F operator. This is a corollary to Wordings inequality. So we have that the inclusion D, which is our domain of F, into L2 is a compact operator. So this follows by simply observing that Wordings inequality and when we write down our Q norm, this is equal to d bar theta plus d bar star theta plus the L2 norm of theta. And this is true for smooth forms, but then we can extend by density. This is true for smooth forms. The point that I'm trying to make is that these all involve either no derivatives or a derivative of order 1. And so just by that, this is going to be bounded by the Sobolev 1 norm up to some constant C1. So what this tells us is actually the norms defined by this Q norm and the Sobolev 1 norm are equivalent, and their Hilbert spaces are equivalent. So actually, our domain for our F is equal to the Sobolev 1 PQ space. And then the compactness of the inclusion of D into L2 follows from Relic compactness. And remember that part of the hypotheses of the Relic compactness theorem is that your space is relatively compact, but our space is compact, and so we can apply it here. Okay. So that ends our digression into Sobolev space theory and begins our discussion of elliptic regularity theory. And these are kind of interesting results to me, just on an anecdotal setting, because I've said these things to some people and they're like, this is really impressive result. And I've said them to other people and they're like, this is obvious. Why do you even need to prove this? So it's sort of based on your perspective and your familiarity with elliptic theory. But we're going to start off with a sort of technical result, or it will look technical. And I'll talk a little bit about the technicalities. I debated not necessarily including this, but I think it's good to see the types of results that you get in regularity theory. And really what this result is going to do is begin our analysis of regularity in terms of regularity in the sense of Sobolev spaces. So you'll notice that the first part of this theorem involves taking a coordinate chart, a smooth function defined on that coordinate chart, and then another smooth function, which is 1 on the support of that guy. And the reason we're doing this is that by our definition of the Sobolev spaces, being an element of a Sobolev space is a local property. It's local, we're on a compact manifold, so when you take it to the entire manifold, you're going to be summing over finite terms, so the same things hold. Okay, so that's why we're allowed to sort of restrict our attention to a coordinate chart. Okay, so now we'll fix a number s bigger than or equal to 0 and let eta be a square integral PQ form such that chi1 times eta is a smooth section. So it's a smooth PQ form. And let theta be T eta. So this is in our domain D of our F, be the unique solution of F theta is equal to eta. Then there exists a constant C depending on S, chi1, and chi, such that, and bear with me for a second, okay. So you might not remember, but we defined, before we got our map F, which we used to define our box Laplacian, we defined this map T in terms of the Riesz representation theorem. So that's where this T comes from. It comes from the Friedrichs construction from last time. So when you read this, what this is a statement is saying that the S+2 norm of our solution is going to be bounded by the S norm of our data, the eta that we started with, plus just the straight L2 norm of our solution. Our solution is going to be L2 because we just showed that our D, or space D, is actually H1, which is included in L2. And so what this is saying is that if the data that we started with was in HS, so our Sobolev space with S weak derivatives, then the solution to this equation is going to be in HS+2. The way that I read this result, so I've written this down in the technicality because this is sort of a standard elliptic regularity result. But the way that I read it is that if the thing that you started with was something that you obtained by taking two weak derivatives, then the thing, there is definitely a better way to explain this. I'm sorry. If the thing that if your data has S weak derivatives, then the thing that you had to differentiate twice weakly to get to your data should have two more weak derivatives. Okay.
May I ask a question?
Sure.
Is that what's called like bootstrapping or something?
Not yet.
Not yet.
That's
okay.
going to come later.
Okay.
Yeah.
Thanks.
Okay. So now we have an actual regularity result in our setting. So we have the next theorem, which is we're taking X to be a complex compact manifold and eta, which we're putting into SPQ XG. We're assuming that it's there. Also here, you'll note that we only showed this for smooth eta, so we restricted eta to being a smooth PQ form. But smooth forms are dense, and so if this holds for smooth forms, then this holds for all forms in HS. Okay. So we're taking here again S bigger than or equal to 0. Let theta be T eta, which is again in our domain D, be the unique solution to F theta is equal to eta. Then theta is in HS plus 2 PQ. So this part follows immediately from the theorem that I wrote above. And then this next thing, in particular, if eta is smooth, and we have that this equality holds in the sense of currents, so weakly, then theta is also smooth. So basically, if eta HS for all S, and then our theta is going to be in HS for all S, and then by the Sobolev embedding theorem, we know that that will embed into the smooth space with, and that all of those derivatives are true derivatives. Okay. Yeah, the bootstrapping comes during the actual proof of the Hodge theorem, which we are getting to. And really, there's only one more result that we need, and it's another sort of big result. And this is so we've had Sobolev space theory, elliptic regularity theory, and now we have a functional analysis result. This is our second after the Friedrichs construction. Okay, actually let me name the theorem first. So this is the spectral theorem for compact self-adjoint operators. And this theorem has 3 parts, and we're going to use all of them. So let T be a map of Hilbert spaces, and we want T to be a compact self-adjoint linear operator. Then the first part is that the set of eigenvalues of T is a subset of R. So all the eigenvalues are real numbers. And further, S has, so S is the set of eigenvalues. S has an accumulation point lambda sub 0 if and only if S is infinite, and lambda 0 is 0. So the only accumulation point that the set of eigenvalues can possibly have is 0, and that only happens when S is infinite. If S is infinite, then it has only one accumulation point, and that accumulation point is 0. Okay. Number 2, the eigenspaces E sub lambda are finite dimensional. And number 3, we have an orthogonal decomposition of our Hilbert space according to these eigenspaces. Okay. All right, and then the last thing isn't necessarily, this is more of a lemma than a theorem, but it's what we're going to use to show that our green operator is compact. And this is that T is compact if and only if for any epsilon bigger than 0, there exists A sub epsilon, B sub epsilon, such that you can write T as the sum of A sub epsilon and B sub epsilon, and A sub epsilon is finite dimensional. While the norm of B sub epsilon is less than epsilon. So here, what we're doing is, we're saying that your operator is compact if and only if you can write it as a finite dimensional piece and then a piece with negligible norm, a very small piece. All right. And finally,
Emily, what do you mean by A epsilon to be finite dimensional? Like, what does it mean by operator to be finite dimensional?
So this is a linear operator of Hilbert spaces, of an infinite dimensional Hilbert space in this case. But it means that the basis for the image of your operator is finite dimensional.
Okay, yeah.
Okay, so now we're going to prove the Hodge theorem. And we stated the Hodge theorem in 3 parts. We're not necessarily going to prove it 1, 2, 3. And just for the sake of time, instead of rewriting the whole thing, I'm going to go back up to where I wrote it down the first time. Okay, so this is the Hodge theorem. We're assuming our space is a compact Hermitian complex manifold. The first part is showing that our harmonic space is finite dimensional and consists of smooth forms. And because this space is finite dimensional, we then get this orthogonal projection, which I've written as small script h sub pq. The second is that for a square integrable pq form, we can find a solution to the equation box theta is equal to our square integral form phi, if and only if the harmonic projection of our form is 0. Also, we say that we know that theta is smooth if our data phi is smooth, and there is a unique theta sub 0 such that the orthogonal projection applied to theta sub 0 is also 0. So that's the second part. And then the third part deals with our green operator. So here we state that it's defined by the identity that our restriction to the harmonic space is 0, and that when you compose the green operator with the identity minus our orthogonal projection and apply it to a data phi, you get theta sub 0 as we stated in part 2, and that this green operator is compact and commutes with box. And we have these other commutations. So we're going to start by talking about smoothness. And here is where we will use bootstrapping. So smoothness of harmonic forms. So suppose we have a harmonic theta, then f of theta is equal to the identity plus box of theta, which is equal to theta is in the kernel of our extended box operator, so that part's 0, and then the rest is just theta. So we know that theta is L2, which implies that theta is also in HS, so this is equal to H0. Sorry, not script. So this is equal to H0, PQ, but theta is now a solution to the equation f theta is equal to theta, which means by our regularity results, theta has 2 additional derivatives, which means that theta is in H2, but then that means it's also in H4, which means it's in H6, which means it's in H8, which means it's in H10, etc. So we get that theta is in the intersection of all Sobolev spaces with s bigger than or equal to 0. And then by the Sobolev embedding theorem, theta is smooth. So our regularity theory and bootstrapping tells us that theta has all of its weak partial, or it's in HS for all s, and then we apply the Sobolev embedding theorem, and that turns those into, well, it doesn't turn it, but it shows us that those are real derivatives or ordinary derivatives. Now we're going to show that the solutions are perpendicular to our harmonic space. So if you'll remember, this is the statement that a form, so we have this if and only if the, wait. Okay, whatever. We're showing that the solutions to this box theta is equal to phi equations are perpendicular to the harmonic space. So the way that we do that is we suppose there exists a solution U such that box U is equal to phi. Then if theta is harmonic, which means that it's in the kernel of box, we have that the inner product of phi with theta is equal to the inner product of box U with theta, which by the self-adjointness property is equal to U box theta, which is equal to 0. So from this, it follows that our solution phi must be perpendicular to our harmonic space if we want there to be such a U. So this is a necessary condition. All right, now we are going to do the work of constructing our system of green operators. So a reminder from the Friedrichs construction, we have that F is equal to T inverse, where T is a map from L2 into the domain of FD, which we've shown is H1. And then we have an inclusion which puts D back into L2. And the corollary that we saw to Wordings inequality is that this inclusion is compact. Also, from the Friedrichs construction, we know that T is bounded, and we have that this holds, this bound, which implies that not only is it bounded, but the eigenvalues of T are bounded above by 1. Okay. Now we define an operator L to be the composition of our inclusion with T, which maps from L2 to L2. And this is a bounded operator. So T is bounded and I is compact. And together, L is compact. So this implies that L is compact. And L is also self-adjoint. Now we have a compact self-adjoint operator, so we can apply the spectral theorem. So by the spectral theorem, the eigenvalues of L form a sequence. So 1 is our first eigenvalue, and then we have lambda 2, and this goes on where lambda m converges to 0. So it's an infinite dimensional space. We have infinitely many eigenvalues. The accumulation of the point of those eigenvalues is 0. And Willie, if you tried to warn me, you're on mute.
Yeah, you have 10 minutes left.
The following orthogonal decomposition. So once again, decomp. This is just from the spectral theorem. We can decompose L2 according to the eigenspaces of our operator L. And again, these eigenspaces are finite dimensional. Okay. So we have that. If we look at the way that we've defined L a little bit more closely, L is equal to the identity composed, or the inclusion composed with the identity plus box inverse. So the eigenvalues of box are the inverse of the eigenvalues of L minus 1. And you'll note that when m is equal to 1, lambda m is equal to 1. So the eigenvalue lambda 1 corresponds to the kernel, the eigenspace K1 corresponds to the kernel of box, which is the harmonic forms. So K1 is equal to HPQ, and this gives us that HPQ is finite dimensional. Okay. Now we can fix bases theta sub j m. So this index is indexing over the eigenspaces and then within the eigenspaces. And for a PQ form, we can write it as a sum over these eigenvectors. So phi is equal to the sum from m is equal to 1 to infinity, and then we have to index within the eigenspace, so this goes from j is 1 to n sub m, c sub j m, theta j m. And finally, we define GPQ acting on our form phi to be the sum from m is equal to 2 to infinity, sum from j is equal to 1 n sub m, c, let me do this. And then we multiply by the eigenvalue inverse, CJM, theta J, M. So I'm going to rewrite this as lambda sub m, 1 minus lambda sub m, but they're equal. So that's our green operator. And because of the way we've written it, it's clear that it commutes with our d bar and d bar star operators. Also, we have that lambda sub m over 1 minus lambda sub m, which is this term here, is bounded above by 1 over 1 minus lambda sub 2. This is finite, which means, whoa, oh no. This is finite, which means the sum converges. Finally, and I mean almost finally, if we look at what happens when we apply our box operator to our green operator, composed with phi minus the orthogonal projection of phi. Also, notice that here we're starting at m is equal to 2. And that's because when m is 1, we're trying to invert 0, which doesn't work. So we exclude the harmonic forms. Okay. So this is equal to the sum from m is equal to 2 to infinity. This sum lambda sub m over 1 minus lambda sub m, c sub j m, box theta j m. But we know what the eigenvalues of box are, and theta sub j m are eigenvectors. That's how we defined this. So this is going to be equal to these sums times lambda m over 1 minus lambda m times cjm, and then this turns into 1 minus lambda m over lambda m, theta sub j m, which is just equal to phi minus the orthogonal projection. So this tells us that when we apply G sub PQ to this guy, we get a solution to box of that equal to whatever. I'm not being very precise, but the idea is that once we subtract off this part, or if this part is negligible, not negligible, if H sub PQ of phi is equal to 0, then box G sub PQ of phi is equal to phi. And that's what we wanted. So the final thing I'm not going to write down, but showing that G sub PQ is compact is just a matter of looking at how it's defined. And you can use that to explicitly write down what your A sub epsilon and B sub epsilon should be, such that GPQ is equal to their sum, and the norm of B sub epsilon is less than epsilon, and A sub epsilon is finite dimensional. So you can just look at it and then figure out how to write it down. It's pretty straightforward, but I'm almost at time and I want to stop for questions.
All right, thank you, Emily. Are there any questions? Right, so if not, basically, right, let's thank the speaker again. Thank you, Emily. So next week, we're gonna have Jacob talking about laminations. Just another reminder that we are actively interested in looking for speakers. So if you're interested, just let me know, or Karina as well. So thanks very much for coming. I'll see you guys next week.
Thank you, everyone.